hurt. Okay, so listen, shut up for a second. I'm going to tell you a tale today about two-dimensional particle kinematics. So back to 2D kinematics of particles. And the first thing that I want you to notice about two-dimensional kinematics of particles is that the x component of motion so the x component and the y component of motion are completely independent of each other. And so you can do these problems. So when you're dealing with your vector equations for kinematics, you could ignore the y part of the equations and just do the x part of the equations, and then go back to the y part, or vice versa. And no matter what, for example, the thing is doing in the x direction, that's not going to affect what happens in the y direction. So for example, if somebody here has a gun, yes, it is.
Oh, he's wearing like a. He's got like a wife beater on.
Yeah, a wife shooter. Wait, that might have not been funny. Sometimes you laugh at things that are not funny. Yeah. Your official position is they're not funny. Okay. Yeah, it looks like a duel right now, but wait. Okay, so it does look like a zombie, possibly. Okay, so this guy shoots a bullet, and this guy just, it looks like a big bullet, but this guy just drops a bullet. It's like an elephant gun. How long does it take for each bullet to hit the ground? Yep. Yeah. So he's shooting this horizontally. And so what's happening here is the only difference in the motion of this bullet and this bullet is in the x direction. The gun is shooting it in the x direction. This one has no initial velocity in the x direction. But in the y direction, both of these are just under the influence of gravity. That's all that's happening. And so this bullet, even though you think of it as, I think most people's intuition is that if you shoot a bullet, it goes basically straight and it's going to take a lot longer to hit the ground than if you just hold a bullet at the same height and drop it. It turns out that you really, the reason you have that sense, I think, is just the bullet is so far away by the time it hits the ground that you don't see it or anything. It feels like it just goes straight, but it really doesn't. It's really going to travel in a parabolic path, and the two bullets are going to hit the ground at the same time. Okay, good idea. Well, instead of testing it, I'm going to show you this video of two people testing. Okay. Okay, so they hit at the same time, and now I'm going to show you this Mythbusters video where they actually do it.
The solenoid. Everything's hot. Let's do it.
Should I use sound?
And after a few test fires and a bit of fine tuning, it works.
Oh, it's good. It's good. It's 1/3 of a millisecond difference. Wow. That's freaking perfect. Let's go do this full scale.
Okay. Which means rolling up the room 360 feet to stake out the drop zone.
So they really just did the experiment, and now they're going to, the only thing they're doing now is they're going to drop the bullet at basically the same location that the other bullet is going to hit the ground, so that you can actually watch them land together.
In the same place and in the same shot. All we need now in the drop zone is Jamie's drop rig. So the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it in the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fire. In 3, 2, 1.
But from 360 feet,
So you could see what happened right there, right? The one bullet was dropped and hit the paper on one side. The other bullet that was shot came in and ripped the streak in the paper.
to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be
The shot we've been looking for. In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than they usually like to make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves.
Okay. So let's see how this works, how the math works, and so last time I gave you the constant acceleration equations. And they look just the same as the one-dimensional constant acceleration equations. It's just you have an x component and a y component now instead of just a single one. So we have px is equal to p0x plus v0xt plus 1/2 ax t squared. And then you have the y equation. And then the velocity ones, we have Vx is equal to V0x plus AXT. And the equivalent one for Vy. And then 2 times AX times the quantity Px minus P0x is equal to Vx squared minus V0x squared. And then the equivalent Y equation. So let's do the calculation, imagining that a bullet is shot horizontally. So a bullet is fired. What's a good bullet velocity? Let's use 1,000 meters per second. Can bullets go 2,000 miles an hour? Okay. I don't know. We'll say it can. Okay. Somewhere in right order of magnitude. So it's fired 1,000 meters per second horizontally. From 1 meter high. Right? Yeah, right. Isn't there a pretty big variation, Siri? So let's change it to 500. That's good enough. What, Ken? Oh. Okay, so the one's fired from a height of 1 meter, just as another is dropped from 1 meter. How long does each one take to hit the ground? Yep. Yes, exactly. Yes, exactly. So the fact that the X and Y component motions are independent of each other means that initial X velocity isn't going to come into this at all. So let's first do it for the case where it's dropped. We can think of that as just one-dimensional motion. We'll have the positive direction up, the 0 position on the ground. Well, so this is the one that's just dropped. Okay, so in this case, it's just moving in a line. You could do it in 2 dimensions. It's just the X dimension is going to have 0 initial velocity. And okay, so what do we know? What do we want? That was rhetorical. So do we know the elapsed time? No, that's what we're trying to find. Do we know the acceleration? Yep. Do we know the initial position? Yep. Do we know the position at time t? do we know the initial velocity? And do we know the velocity when it hits the ground? We don't, but we don't care. If we can get by with this, no problem. Okay, so what equation works? It looks like, yes. So yeah, P is equal to P0 plus V0T plus 1/2 AP squared. So we have 0 is equal to 1 plus 0T minus 4.905 T squared. So T squared is equal to 1 over 4.905. And so T is equal to 0.455 seconds, right? I think so. Yeah, is that what it is? Square root of 2 over. That's okay. So that's how long it takes if you just drop it. So now let's do the calculation where it's fired out of a gun. So this time, what do we have to choose? So like in 1D, we had to choose the 0 position in the positive direction. This time we have to choose an origin location and an orientation. Yep. Well, I'm just showing how they mathematically how they come up independent. Okay, we're just going to see that the x component doesn't come into it at all. You're exactly right. Like we're going to get that same number because the equation is going to look the same. Only the y equation is going to matter. Yep. And so we'll put the origin on the ground beneath the start point. And we'll put the y-axis up and the x-axis horizontal in the direction of the shot. So based on these choices, let's think about what we know and what we want. Now we have to go through 13 variables instead of 6. Sort of a pain. Okay, so do we know the elapsed time? That's what we want. Do we know the acceleration? What's the x component of the acceleration? That's a velocity. Acceleration is just 9.81 meters per second squared down. So that's right. So no x component of acceleration. Only because of air resistance. Right. So I want to talk about that after this is over, but it turns out there's a lot of air resistance. There's very little air resistance in the y direction. And so our answer is accurate for how long it takes to land, even though our calculation of how far away it landed would be off. Yeah. It's just going so fast. It helps, but it's just going so fast. There's a lot of air resistance. Yes. Then, except you'd have to have someone shooting it. But he could wear an oxygen mask. Spacesuit. Okay, so AY is negative 9.81. Do we know the position, the initial position? There's X and Y components. 0 and 1, yep. Do we know the position at time t? We don't know the X coordinate. We don't know the X component, but we do know the Y component. So Py is 0 because it's on the ground. Do we know the initial velocity? For the initial velocity? Yes. So V0x is 500. Yeah, so so this is the initial velocity when it's launched. Okay? Do you all agree that that's the velocity vector at the instant that it's shot? Okay, and so, yep. Yes, thank you. Okay, so if that arrow represents the velocity, then it's just a matter of figuring out what the components of that vector is. It has a magnitude of 500. It's totally in the x direction, so the components are 500, 0. If this angle was different than 500, you'd have to use cosine and sine to figure it out. Okay. You can still use cosine and sine because 500 times cosine and sine is 0, which is 500, 0. And do we know anything about the final velocity? Okay, so be careful about that. These equations only work while it's in free fall, while there's constant acceleration. So once it hits the ground, we can't say anything about that. So the ground will stop it, but by then we're done with the calculations. So what we want is, we're asking about the velocity just the instant before it hits the ground. And we don't know that velocity. It turns out that, like, notice there's no x component of acceleration, okay? And so actually the x component of velocity is going to stay the same, but we're going to pretend we don't know that. That's more cocktail party banter than part of our calculation. The x component of velocity is constant. Yes, and because we're assuming no x component of acceleration. Right. Well, so I just told you everything you need to know about that particular cocktail party discussion, but don't use it in the calculation because it'll confuse. It'll make you think you know stuff that doesn't end up helping you and stuff. Yeah, right. Okay, so is there an equation we can use to find p? Yep, the y component of the same one. So we're going to use the equation that says p y is equal to p0y plus v0y t plus 1/2 ay t squared. Yep, and everything comes out exactly the same as it did in the first case. Yes, thank you. I totally agree with my spokesperson, Jill. She's right on with this. So I'm just showing how, like, if you do it as a full 2D problem, the x component just doesn't come into it. You end up, it reduces to the exact same equation we had when we dropped it, and so the times are exactly the same. Question? Okay, so this equation comes out to say 0 is equal to 1 plus 0 minus 4.905 t squared So t is equal to 0.455 seconds. It's the exact same equation we had before. So the x component information never even came into it. Never even came up. Right. And so the way these two components can relate to each other is, what if you wanted to calculate how far it traveled before it hit the ground? How far horizontally it traveled before it hit the ground? Okay. Well, the way you would do that is you'd figure out the time that it takes to hit the ground. And then you take this time and plug it into an x equation. You use the y equation to figure out what the end of your interval is. Then plug that into an x equation. So let me do an example like that. Question? Yep, that's right. So how far away will the bullet hit? And I'm talking about horizontally. So we'll plug the t from the y equation yeah, exactly, into the x equation. So we're going to use the equation that says px is equal to p0x plus v0xt plus 1/2 ax t squared. Right, we want to find px, right. So let's fill these values in. Px is what we're trying to find. P0x, what was that? 0. What was V0x? Yep, 500. T is 0.455. What's AX? 0, so this goes away. And so PX is equal to 277.5, something like that. Yes. 2. So anyone, you guys got one of those digital hand calculating devices? 277.5? No! Kind of. Yeah, exactly. That's what counts.
This number is like completely useless in any real life situation, right?
Okay, so that number, so let me say something about that number. Our time of 0.455, if you dropped a bullet, would be very accurate, okay? It would be very accurate because the bullet never gets going very fast, you know, as you drop it. Okay. So what about that time 0.455 for when you shoot the bullet? The bullet's going really fast. You'd expect there to be a lot of air resistance. Do we trust that number 0.455 for when you shoot the bullet? Yes, that number is still pretty good because what air resistance pushes exactly opposite the velocity vector. And if you think about this thing's going so fast horizontally, think about the direction of the velocity vector even when the thing hits the ground. It's still almost horizontal. Okay, you be quiet. Quiet, you. So even though there's a lot of air resistance, almost all of that air resistance is acting horizontally. Very little is acting vertically. And so even with the bullet being shot, that 0.455 seconds is a good estimate. As good as it was for when you dropped it. This is probably a very bad estimate because there's a ton of air resistance horizontally. And so, we'd have to deal with that. This is what would happen inside that vacuum chamber. Okay, so now about lift and stuff. If you're inside that vacuum chamber, there's no such thing as lift. A helicopter in that vacuum chamber has a downward acceleration of 9.81. Yeah. You really need me to pilot this experiment? And so same thing. So if a bullet had lift outside of a vacuum, then all of these answers would be wrong. This stuff only applies in the case that air resistance is negligible, and lift is just a form of air resistance. It's air resistance that you're harnessing for a useful purpose. Yeah, right. I don't think there's anything about a bullet that gives it lift. I think rifles spin bullets, right? And I think that spinning helps keep it oriented. And so what? Yeah, well, that's just round, right? Me neither. I just thought of a word related to guns. Yeah, that's about how much I know about it too. But like a rifle spins it so that it stays oriented in an aerodynamic direction. Whereas if it's not spinning, it can just tumble like a knuckleball, Yes, that's true. Okay. So now, let's do the same thing, but this time, holding a gun perfectly horizontally is hard, right? I mean, you can't get it perfectly. So now let's do the same thing, but calculate So we're going to calculate the same two things. First, the time to hit the ground. And second, the horizontal distance. If the bullet is fired 1 degree above horizontal. 1 degree is very little, right? That's not even really visible. What do you think is going to happen with this? Yep, that's right. So, yep, exactly. So the way to do this is you're going to do the y calculation to get a time, then plug that into the x. So will you guys come up in groups and do this on the board? And now it's my time to shine. That means They be quiet. They're not listening. Okay. So the next thing is there was something in 1D kinematics where you knew that if the velocity was equal to 0, well, you knew that if the thing was changing directions, get to the top point of on a ramp or the highest point in a flight in free fall, the velocity was equal to 0. Anybody have a thought on what the equivalent of that would be in 2D? So in 1D, when something gets to the highest point in its flight, we set the velocity equal to 0. That's how we knew it was at its highest point. How does that work in 2D? Yes, that's perfect. Yep. So the y component of velocity has to be 0, not the x component. Okay, so does that make sense to everybody? So a lot of people, like on the first thought, you would think, okay, well, we're just switching from scalar values to vector values, so at the highest point, the velocity is equal to 0. But it's not how it is, and I think it's pretty clear if you imagine let's see. Okay, so this guy, this gorilla, throws a ball. Okay, it follows a parabolic path, and here's the highest point in its flight. Okay. And if the velocity was equal to 0 at the highest point, if the entire velocity was equal to 0, it would mean that you could set up a ladder here and stand up on the ladder. On your head right where that ball's coming. And if the entire velocity vector was equal to 0 at the highest point, it means this ball would just gently nuzzle up against your head, reach exactly 0 velocity right there, and it might feel nice and tickly or whatever against your hair. But that's not how it works. You would definitely not want to do this, So if you ever get confused about the requirement for reaching the highest point, remind yourself about this, okay? The velocity vector isn't 0. It's only the y component that's 0. It's not, at this instant, it's not going up or down, but it's still cranking horizontally, But don't do this experiment because you might think like it'd hurt, but at least I'll learn, but you wouldn't remember the experiment even. So it's a lose-lose.
No, you just put someone else there.
That's true. When my little brother was 2 years old, me and my friend were out at a tennis court with a tennis ball launcher, shooting like pop flies. We were standing on the other side and like catching tennis balls. And my little brother like waddled over and he like saw one go and he was like, "What's in there?" And he just totally like looked. We're like, no, looked straight down the cannon. It was on full speed and just took tennis ball right in the eye. I would never say this to my parents, but secretly it was kind of funny to watch. He didn't get a black eye or anything, but it knocked him a long way, Okay, let's do one more example. Okay, so here's the question. So say that there's this basketball player shooting a ball. And that's the end of a shot. You just do it with your wrist, and then you stand there like in your face. Yeah. Oh, I see. No, that's not how I meant it. Okay, the hand thing, that's not relevant to this problem. Okay, so let's say that he releases the ball at 1.5 meters from the ground. And this distance is 4.572 meters. That's 15 feet. That's the free throw line. The height of the basket is 10 feet. So that's 3.048 meters. And let's say that the ball is released at an angle of 45 degrees with the horizontal. So first, what's the required speed that the ball has to be released to go in the basket? Yeah. And second, what's the highest point? What's the height of the ball at the highest point? Yeah, 3.048. Yeah. What's the height at the highest point?
What about the back? Is there no
Backboard? Right, no backboard. It's just, that basket's being held up by drones. Okay, so see if you can work through this one as groups.